Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start with the lecture number 13, and in this lecture we will discuss about instructions execution, flow control instructions, and stack related instructions. Before starting this lecture, we will discuss that what we learned during the previous lecture, that was lecture number 12. So in lecture number 12 we did some programming in assembly language, and the operators and the topics that we covered were like offset operator. This offset operator we used to return the offset address or the distance from the data segment and so on. So it returns the distance of the variable or the label, and then pointer will give us the address, and it overrides the default data type, so we can access part of the label or the variable and so on. And then there was a type operator. This type operator just gave us the type, that what is the type of the variable. For example, if we define byte, word, double word, quad word, so it gives us or it returns the value in terms of bytes. For example, for byte it will return 1, for word it will return 2, for double word and so on. So 4 and 8, whatsoever the type of the variable is. Length of operator, we discussed about length of operator, and we saw the examples regarding the length of operator. It just gives us the total number of elements, that what are the total number of elements inside the inside an array or inside a label and so on. Then the size of operator, as we discussed, the size of operator is the combination of two. It will return like type multiply with the length of. So what is the type? For example, if we define a word, and the word for example array 1 is of size is type word, and then we define multiple elements, so for example 4 or 5 elements. So length of operator will just give us how many number of elements. For example 4 elements. Type operator will give us the what is the type, like word is 2, so it will give us the total number of bytes that this variable occupies inside the memory. So 4 multiplied by 2 is equal to 8. So total size of this variable array 1 inside the memory is 8 bytes. So this was we also saw some examples regarding the size of operator. Then we saw also the label operator, that we can use label directive to access the variable or the memory location which is reserved for any variable or something. So we can give another name to that memory location, just like in the pointers. So we can give another name to that memory location, so we can access that memory location with another name and so on. Then we also discuss about the indirect addressing, like indirect operands. So we could use the indirect operands, and we saw also the array some example. So indirect operands we just use like we have label plus some pointer or offset here, so we can get the total address or the complete address. So indirect operands we just use for example ESI, where register, it was assigned the address. It was assigned the address of some, or we can call it offset of some variable, for example array 1 or something. So we just move this one, the offset in ESI, and we just use this ESI to access the same variable and so on. So this was called the indirect. So then there was indexed. In the index operands we use index value label and the index value. And then we also saw there was another representation for this index scaling, like label, or we can call it variable. So this was label plus something. Now we have got the variable and the register or something here. The index was at this point. So this was another representation for the index operands. We also discussed about the scaled index. That how we can use a scaled index inside our assembly language. Then in the end we also discuss about the pointers. Now in this lecture, the topics that we will discuss include the instruction cycle, program execution, control flow, and in this control flow we have jump and loop. So these two both instruction we will see separately, what is jump, what is loop, and we will see the examples of jump and loop. And then the complete program about summing an integer array. This is the same program which we did in the previous lecture in assembly language, or in lecture number 11 also. So we just sum up all these elements inside an array. So here in this lecture we will try to do that one by using jump or loop instructions. Then in the end of this lecture we will also discuss about the stack operations. So here in this lecture we will discuss all these examples and everything. Then inshallah in next lecture we will discuss how we can program, how we can write all these examples inside assembly language to see that what is the output of all those programs, so we can practically analyze all those programs which we are writing, or the logic which we are discussing right now. We will see them in practice. Now before starting, I want to revise something that is a basic slides in the initial lectures, like what is microprocessor, what are the components and everything. So only 1 or 2 slides, so it will not take that much time. So there are multiple. This is the basic microcomputer design, or microprocessor or computer architecture or design. So there is you can see here we have the clock. So clock is somewhere here, or it is possible that clock is outside so for example this is the central processing unit, or we have the microprocessor. This one is microprocessor, or we can write it like this one. So this is microprocessor, and then there is also a clock inside the microprocessor. So this clock, it synchronizes CPU operations. How? For example, we are going to access memory, we are going to access the input output devices, or we are performing something inside the some operations inside the central processing unit. So this CPU, the clock, synchronizes all we will see in the next slide what is a clock and how does it synchronize. So synchronization means to continue these operations in a systematic manner. So there should not be some mess up and something. So it synchronizes all the work, like every part work along with the other parts without making any trouble. So, and then there is a control unit. This is the most important unit that coordinates between all these elements, and it performs the sequence of execution steps. How? For example, if we want to execute an instruction, now what will be the first step, what will be the next step, and what will be the control signals, so to perform all these operations. We will see one example when we read data or write data inside memory and so on. So what will be the control signals and so on. And arithmetic and logic unit, as we know that it performs arithmetic and logical operations, are bitwise operations. This is just simple overview. This is the CPU, the simplified block diagram, and here you can see we have the code cache, instruction decoder. So this control unit registers ALU, data cache, floating point unit, and instruction pointer. These code cache or instruction and instruction decoder, they were not discussed in the previous slide, so I'm trying to make it more discuss in depth, so you can understand how we execute complete instruction, when we execute one instruction or two instructions or multiple instructions, how these operations are being performed. So these are the components. We have the instruction pointer, and then we have the instruction decoder, and then we have cache, code cache, and then we have memory. Here you can see we have one memory, and this memory is used for code and data also. Definitely if we are accessing anything like input output devices or maybe the memory and so on, so there should be data line and there should be address lines and so on. Similarly, there should be some control lines. Here there are not control lines from here to here, but it should be there. So there should be control lines to synchronize all the components. And we have floating point unit. If we perform any floating point operation, then floating point unit is part of this microprocessor to perform all these operations and so on. Now clock, as we know that this clock synchronizes all CPU and bus out all computer operations. So this clock is nothing but the sequence or the pulses. So these pulses like start from here, and so this is, for example, if we start from here from this point, so this is called the complete cycle from here, and from this is called the trailing edge, and then this one is called the leading edge. From here, if it comes from top to bottom, so we can call this one is called the trailing edge, and here you can call it the leading edge. So this is a complete cycle. So this is whole or complete cycle, that one cycle, so minimum one cycle is required to execute instruction. Depends, some instruction takes more than one clock cycles. So instruction cycle is combination of multiple clock cycles. So one single operation like instruction decoding operation will be performed maybe only by using one clock cycle, or fetch operation takes only one clock cycle, decode operation maybe it takes one operation or one clock cycle, it takes multiple clock cycles and so on. But at least to perform any simplified task, computer needs clock cycles. So based on these clock cycles, the whole operations are being performed by the CPU. So machine clock cycle measures the time of a single operation. So a single operation is measured like by using these clock cycles. So this clock is used to trigger events. For example, whole instruction, there are multiple parts inside the instruction execution: instruction fetch, instruction decode, instruction execute, fetch, decode, execute, and write back. So there are multiple steps. There are also other steps like fetch, decode, execute, and write back, or sometimes we call fetch, decode, fetch operands and execute, and then write back, and so on. So there are multiple stages to perform whole execution of the complete instruction and so on. So each step can take more than one or minimum one or more than one clock cycle to complete that task. So this is the clock cycle. You can see complete clock cycle from here to here. This is one cycle, and then this is another cycle from here to here, then third clock cycle. So this is 1, 2, 3, and 4 clock cycles. Now it depends on different architectures that either computer or CPU perform operation on leading edge or trailing edge. So depends on the architectures and so on, and the implementation. So this topic is not related with this subject, but this is the main topic when you study computer architecture in more detail. So we will not discuss that one in more detail. So just for the concept, so computer or CPU performs operation based on the clock cycle, either based on the leading edge or the trailing edge, and so on. Now, instruction cycle. Now, inside the instruction cycle, there are multiple components that are involved, which are part of the complete system. Like, for example, each machine language instruction we fetch from the memory and store it inside the instruction register. We fetch from memory and store inside the instruction register. Now, you know that instruction is read from memory. Instruction is read from memory. So we read by using, first we select some location inside the program section or program segment. So we select the address, and from that address we fetch the instruction. Now it depends, either we fetch complete instruction or part of that instruction. Whatsoever we fetch, initially we fetch opcode and so on. So we fetch instruction, we are not going to specify what we fetch first, but initially we fetch instruction. Simply we can call it we fetch instruction and move it to the instruction register, or simply is called IR, instruction register. So when we fetch instruction, so this instruction can be add instruction, move instruction, and so on, or subtract instruction, and so on. All those instructions that we have discussed, and also all those instructions that we will discuss in future. So all these instructions are part of the program memory, or the code segment, or the code area where code is stored. So we fetch them first and put them inside the instruction register. Now, what is the next step? The next step is the address of the instruction to be fetched is stored in the register called the program counter. So actually the first step is to address from where we want to fetch. So we have the program counter register. So initially this is the first step. We know that what is the address from where we have to fetch the instruction. So this is the part, or this main responsibility of the program counter. It depends. In some architectures it is called the program counter, and in some architectures it's called the instruction pointer. So don't be confused. These are the two names for the same register. So instruction pointer or the program counter. So the instruction that is to be fetched, means, for example, before fetching instruction we must know, or the program counter must contain the address from which we fetch the instruction. Okay, then when we fetch the instruction we move it towards the IR register. So after instruction is fetched, the program counter or the instruction pointer is incremented. So program counter or instruction pointer is incremented. We increment. Now this is 1 byte increment, 2 byte increments, 3 byte increments, and so on. We don't know, because it depends on the instruction. Some instructions are 1 byte, 2 byte, 3 byte, 4 byte, and so on. In case of these the instruction set are CISC, we are discussing right now. So in case of all the instruction we studied in previous lectures, so these instruction can be 1 byte, 2 byte, 3 byte, and 4 byte whatsoever. And there is another architecture that is called the RISC architecture. Inside the RISC architecture, all these instructions have the equal size. Equal size means whole instruction is 32-bit in RISC. In CISC it depends. Instruction can be 1 byte, 2 byte, 3 byte, and so on. So there is some difference. Now here, in case when we don't know what is the instruction, what is the length of the instruction, it is 1 byte, 2 byte, 3 byte. So depends on the instruction, program counter will be updated accordingly. If the instruction is 1 byte, program counter will be incremented by 1. If instruction is 2 bytes instruction, then program counter will be added 2. If instruction is 3 bytes, 4 bytes, and so on, so program counter will be added accordingly. But in case of RISC, when we know that each instruction is 4 byte instruction or 32 bits instruction, then automatically the increment or default increment inside the program counter is 32 bits in case of RISC. Now, one thing, here we are discussing only the few steps, but you know that when we execute a program, our program doesn't flow in doesn't follow the sequence like first instruction, second instruction, third instruction. As we know that when we use for loop, while loop in C, so program flow is disrupted. So we are not following the conventional flow from top to down and so on. So we will discuss in the next slide, few slides, when we discuss about the program control flow and so on. So it depends on the instruction what will be the value in the program counter, so which next instruction will be executed and so on. So this fetch instruction is decoded. First step, program counter has the address. From that address, next step is we fetch the instruction and put it inside the instruction register. Third step is that we decode that instruction. So we determine that what needs to be done. So when we decode, then we don't decode, but when CPU or the microprocessor decodes the instruction, it sees what are the combination of bits inside the instruction, what are the unique number of bits. So based on these unique numbers, if you recall that we discussed, or I told you that instruction set architecture or instruction set has multiple instructions, maybe hundreds of instructions, and each instruction has unique bit string or bit sequence. So computer can easily recognize that which instruction to be executed, or what is the purpose, or what is the operation of each instruction. So that is determined when we decode the instruction, and after decoding, the operations are being performed by the CPU. So this is called the execution. So before execution, maybe we need to fetch operands. So instruction fetch, instruction decode instruction, then we need to fetch operand. Might be some instruction needs operand to be, like if we want to load something, or if we want to perform addition, but before performing addition we just move value in the indirect addressing. We move value from memory somewhere and then perform operation, so we have to fetch operands. So this is complete instruction execution cycle. You can see instruction fetch, instruction decode, operand fetch, execute, and then the last step is write back. For example, if we perform addition or something, or some other operation, maybe the logical operation, arithmetic operation, bitwise operation, or so on, so we write back the results. For example, if we add two register A and register B, for example AX and BX, or might be EAX or EBX, RAX or RBX, and so on. If we perform some operation and result must be stored somewhere, so we can say that this is the last operation, like A is added with B, and again result is stored in A. So this is the operation, the last operation, that result is stored inside the A, or maybe result is stored somewhere inside memory and so on. So this is called the write back phase, or the last phase here. So all these steps are defined here. So obtain instruction from the program storage, then determine the required actions and instruction size whatsoever. So based on these instruction size, we decide what should be the increment inside the program counter or the instruction pointer. And then third operand, locate and obtain operand data. What are the operands we are using inside the instruction. Then fourth operation is compute result, value and status. When we compute or perform operations, and we also monitor the status, we have the flag registers and so on. So, and then the last operation is deposit results in the storage for later use, either in memory location, either somewhere else inside the registers or so on. So here you can see this is complete execution cycle, instruction execution cycle. And here you can see the first step is instruction fetch, instruction decode, then operand fetch, instruction execution result write back. Again, next instruction starts from here. So instruction fetch, again start instruction fetch and decode and so on. So this is complete execution cycle. Now this is the timing diagram. Now we know that there's a clock, there are address lines, there are data lines, and we know that there is memory and so on. For example, assume that here is RAM or memory. So we have memory here, and there are some address lines, and we have data lines, and we have also some control lines and so on. So this is the clock. So you can see this clock is like this one. This is actually, all the clocks are not like pulses, like this simple pulse like this one. So actually they are represented like this one. There is a slant, the slanted line is at the leading edge and the trailing edge. But here you can see this is a complete cycle starting from here and ends here. So this clock, and this is the timing diagram, how memory read cycle, how we read data from memory. So this, after reading data, maybe this value is being transferred to the register or so on. We are not concerned, we don't know that where this data will go and so on. So this time, if we know, then this timing diagram will be further extended. But to show you the example that how CPU performs these operations and what should be the control signals and so on. This is a simplified timing diagram, because we know that there is a clock, there are address lines, there is control lines and data lines. Here you can see in the first cycle, what we do, we put address here. This cross means previously there was some another address value on the address lines. So now there are address lines, for example 20 address lines or so on. So on these address line there was another value. Now after this one, when during this cycle we update with a new value. New value has been updated in the first cycle. And read is high. Here read is high. So and during this cycle read becomes low. So this will be, for example, this is the control signal which determines that to perform read operation, and this read operation will be performed when the signal is low. So this is the baseline, for example. This is the baseline. So just like here, when the signal is low, operation will be performed. When signal is high, some control lines depends, either they are complemented or not and so on. So if you know the digital logic and design or some subjects, subject related to the digital logic or something, so you must know that the truth table and how to see all this, how these signals work. So for example, if it is low, then it will take the action. For example, read action will be performed. Now how in the first cycle we put address, in the second cycle we say that now read. So read operation will not be performed in the second cycle. We just send the control signal in second cycle that now perform read. So this is control signal. Now here you can see previously whatsoever the data was in data lines, now new data will be updated in the third cycle of the data lines. And then what we do in the fourth cycle, we again convert or change the read signal or read control signal. Maybe there are some other operation that will be performed. So this is how we read. First we set address, then in the next cycle we set that perform read operation. In the third cycle the data is read from the memory location and put it sent over the data lines. So this is timing diagram. Now you can see this is only for the read or read from memory. So memory read cycle. Now memory write cycle is something different. Okay. Similarly, if we want to simulate, if we want to show a complete execution of our program or complete execution of the operations or complete operations of a microprocessor, so we can show them all in the timing diagram and so on. So when people design microprocessors and the instruction set architecture, they design all these timing diagrams and so on. So it's very easy to understand what's going on all these pins. For example, every microprocessor had number of pins. For example, clock pin, address pins, control pins, and data pins. So you can, if you know what is the purpose of each pin, then you can easily say that what operation will be performed inside this. So this is the same thing. So program counter has the address. This is program memory, complete program memory. There's instruction 1, 2, 3, 4, and so on. So this program counter has the address of the current the next instruction to be executed. So for example, next instruction is instruction number 1 that is being executed. So instruction 1 has been fetched, then it is going to put inside the instruction register, then it is decoded and executed. So before executing, maybe we need to read the operands from the memory, read operands from memory inside the registers and perform some arithmetic and logic operations, and based on these arithmetic and logic operations flags are being updated, and then maybe it's possible that values are being stored inside the registers, or maybe values are written inside the data memory and so on. So this is the complete cycle. I think now you can understand what are the registers which are involved in read cycle, write cycle, or it means in complete instruction execution. Inside the program, when we will write all these simple programs, then I will show you that what are the values for the program counter register or the instruction pointer and the all these registers which are being involved and so on, and how we can see that where our program is stored and in what format our program is being stored. Okay. So program execution, so CPU loads and executes programs sequentially. For example, instruction 1, instruction 2, and instruction 3, and so on, for example. So all these instructions, each instruction can be of different size in CISC, but in RISC, I'm just going to repeat, the size of instruction is 32 bits, so 4-byte instruction. So each instruction is in RISC. In CISC, its size is different. So it is possible that the instruction might be conditional, or instruction doesn't follow the sequence like instruction 1, 2, and 3. So it is possible to transfer the flow control. So this is a sequential flow control. It's possible that we move from this instruction and perform another instruction somewhere here, or maybe we are here and maybe we move on the other side or somewhere else inside the program. So the conditional instruction or conditional control transfer instruction or transfer control instructions, so they transfer control to a new location inside the program based on the values of CPU status flags, 0 flag, sign flag, carry flag, and so on. So if we say that if some value is less than this one, greater than this one, or if it is the result is 0, if the result is less than 0, greater than 0, and so on, so we perform this conditional or transfer control. So we perform looping, jumping, and so on. So these are like the if statement. If this thing happens, then go to this one. If this is the condition, then go here, and so on. So these are the instructions which we use. So this transfer of control or a branch is way of altering the order in which statements are being executed. So there is another way. For example, if we say it's possible that condition is true, then we jumped to somewhere else in the program. So they alter the order. They don't follow the sequential order. So transfer of control or branch, there are two types. One type is unconditional and conditional. So in unconditional, they transfer control whatsoever the logic is, nothing, they just transfer control. When program comes to that instruction, it just transfer control, and so on. In conditional, they transfer control based on some condition, as we discussed. If value is less than 0, if value is greater than 0, if value is less than another value, or so on. So after comparing two values, or after getting the result of the operation, like sign flag and carry flag and the other flags, so we say if value is less than 0, or if value is 0, then transfer control. If it is greater than 0, or greater than or equal to 0, less than or equal to 0, then transfer control. So if this condition satisfies, then program control or transfer of the control is performed. So we break the normal sequence, or we branch. Otherwise we do not branch inside the, or we do not transfer control to the another location. So unconditional, it doesn't matter. When program come to that instruction, it will automatically transfer control, and so on. Here the first instruction is the jump instruction. So jump is the unconditional jump or unconditional transfer of control category instructions. So jump is unconditional jump to a label that usually within the same procedure, inside the same procedure. So we will discuss about procedures. So right now we are not using the procedures and so on. So for example, if we write a program, what is the syntax? Syntax is jump, and this is a target. Instruction pointer or the program counter will have the target, or the whatsoever the address is given to the or assigned to this address. For example, if I write here ABC double dot move EAX comma val1 aid EAX comma EBX, and if I say jump ABC, okay, so jump ABC. So what will happen if programs comes to the, okay, now before going to do something or discussing this one, just look at here. How many instructions are there? 1, 2, and 3 instructions. If there are 3 instructions, then they must be assigned some memory inside the program segment, or we can call it code segment. So ABC, actually move instruction will have some, it is opcode, and so it will be converted into the hexadecimal and something. It has the sequence or unique sequence. So for example, if this is 1 byte or 2 byte instructions, there should be some starting address, and here be the starting address like 2001 and so on, 2002, 2003, 2004, and so on. So one byte instruction, for example this one byte instruction, this one, and so on. This is multiple byte instruction, for example. So this starting address is identified by this label ABC. So when program counter comes to 204, for example, or something, to execute this instruction, then program counter will not be updated here in this direction. Program counter will be assigned a new value of this this location, which is being identified as a B, C. So we will do programs where you will see that when we write jump, then it has some mnemonic, the mnemonic is jump, and it will have some hex code, for example any 6x or whatsoever the 6a 6b or whatsoever the in hexadecimal. So it has some hexadecimal code, and ABC will be identified as an address of the instruction, like this instruction. Whatsoever the address is, that where this move EAX comma val 1 is stored, so this address will be replaced with the ABC will be replaced with that address. So this is the jump, unconditional jump, or you can call it, this is the unconditional transfer control instruction. So there is no condition that either it's something we're comparing some value or not. No, there's no condition at all. So without condition we jump. Okay, we will see the examples. So instruction pointer or program counter, don't be confused, they are same. Okay, and then we have another instruction. There are so many instructions. Right now we are discussing only few. We are discussing jump and loop only for this during this lecture. In the coming lectures we will discuss other conditional transfer control instructions. There's a huge list, but we are only discussing few of them, only two of them. So the loop instruction creates a counting loop. It has some condition. Based on some condition, it has the it start the transfer control. For example, what is the syntax? Loop and target. Now there is no condition involved here, you cannot see any condition, but actually what is the logic behind this one? So the ECX register, for example, before starting loop, what we do, we assign any value to ECX, and every time when loop is called, we subtract 1 from ECX, and we see if ECX is not equal to 0, then jump to the target, until and unless ECX is not equal to 0, then it will jump to the target, and so on. So for example, if we assign positive value 5, so initially it will see that it is 5, so it will 5 minus 1 will be 4, so it will transfer control because 4 is not equal to 0. So again, when the next time it will come, it will decrement one more time, 1 from the ECX. So initially 5 minus 1 is equal to 4, 4 will be assigned to ECX, then 4 minus 1, 3 will be assigned, so it is decremented and compared. So when it will become 0, then it will not perform any jump. Now here we are not, the condition is not defined, but it is indirectly at the back end side. We define the value of ECX to control this logic, that how many times this will continue. So implementation is that the assembler calculates the distance in terms of bytes between the offset of the following instruction and the offset of the target label. So this is called the relative offset. You know that we calculate the addresses. For example, program is stored, as I told you in previous slide, that each instruction has a starting address. In case if instruction is multi-byte instruction, multiple bytes are there, so each instruction has address. And for example, currently program counter or instruction pointer is here, and it is possible that we can jump at this point. Maybe we can jump either from here, we can jump here, or we can jump in this direction. It depends. Where is the label? If the label is at the bottom, it will increment the program counter, or it will add something. If it is on the top, like before this instruction, we're moving here, then the program counter will be subtracted and so on. So assembler calculates the distance. So this distance bit from the label, from the current pointer to the label, is being calculated, and we add or subtract. So either we add or subtract. So where we are going to perform, so this is the distance, the same distance is here and same distance is here. So we calculate distance from the current program counter value, not the current program counter value, but the current instruction that is being executed. So what will happen when current instruction is being executed? Program counter has already the next instruction address. You will see when we execute instructions, so the program counter will calculate the distance from here, from the next instruction to be executed, either in upward direction or in the forward direction or the downward direction. So depends. So the relative offset, either it is added, so definitely it is added. So in case if it is subtracted, it is not subtracted actually. We convert into the 2's complement, and again we add. So this offset can be positive and can be negative and so on, which we calculate. That is called the relative offset. So for example, we have the loop example here. You can see this is the machine code. This is the machine code. Here, this is the source code that we always write inside the assembly language when we do that one in Microsoft Visual C++, 2010 Express Edition and so on. So this is the source code. Here you can see this is part of the program. There is data and there is code and whatsoever. The instruction, this instruction is stored here. Next instruction is stored here. So this is the offset. You can call it, for example, address. This is the address inside the program area. Our program is stored in this area. So maybe our instructions are upward and also stored here and so on. What will happen? You can see here 1 byte, 2 byte, 3 bytes, 4 bytes. Starting from 00, 00, 01, 02 and 03. These 4 bytes are assigned to move AX, 0. So this instruction is 4-byte instruction. What about the next instruction? Move ECX 5. So this is 1 byte, 2 byte, 3 byte, 4 byte and 5 byte, because the instruction is same. Only the difference is here, this value 5 is how many bits how many bytes value? This is the 32-bit value. Here 0 is 16-bit value, because we are referring only 16-bit register. So here you can see this is 16-bit value. Here this one is the 32-bit register and so on. So we refer ECX, so this is 32-bit register. So this value is 32-bit value. So B9 and then this all this. So what about this instruction? 1, 2, 3, 4, 5-byte instruction. Same move instruction, same register. But here the register, accumulated register, is referred as a 32-bit register, not 16-bit register. Okay, just come to the next one. So 5 bytes. So 5 bytes after this one. So 4th address 004, 5, 6, 7, 8. So all these 5 bytes from 4 to 8, all these 5 bytes are assigned, reserved to store only one instruction. For the first instruction, only 4 bytes. And now just come to the next instruction. The next instruction is add AX, CX. So add instruction is this, add AX, CX is 3-byte instruction. Add AX, CX is 3-byte instruction, 1, 2 and 3 bytes. So 9, then A, B, 9AB. So it's like 8, 9, A, B, C, D. So this is the hexadecimal counting. So address number 9 and address number A, address number B. These 3 bytes are allocated to this instruction only. So this instruction is 4 bytes, 4 byte instruction, 5 byte instruction, 3 byte instruction, and this one is here, for example, it is 2 byte. Actually it is not 2 byte. It depends what is the address. If address is 20, offset is 32-bit offset, or offset is the 16-bit offset, depends which architecture we are programming and so on. Just assume that this offset is the 8-bit offset or something like that one. So what we do, we have to jump. So this instruction starts 8 instruction, this is the starting location, starting address. This address is shown by the L1, label L1. Label L1 shows this instruction. Now what will happen, we are at this C or 00C, we are like 3 more instructions, 3 more bytes back is a loop. Now when this instruction is being executed, when we execute this instruction, actually the program counter has this value. Program counter, when this instruction is in execution phase or execution, then we already calculate the program counter value or instruction pointer value. Instruction pointer value. So program counter or instruction pointer, their value will be like this one, 0E. Now we know that current value of program counter is 0E. Now if we perform loop to L, or we want to jump to L, or we want to jump to this address, then we have to subtract. What we have to do, we have to subtract how many bytes from 0E hexadecimal. At least we have to subtract 3 byte this one and 2 byte this one, 5 bytes or 5. We have to subtract 5 from here, then we can go move toward the 09, sorry. We can move towards the 09 address and so on. So we have to subtract 5, minus 5, then we can come to this address 0, 0, 0 and 9 and so on. Okay. So this minus 5, for example, is shown as a 2's complement or in hexadecimal. So this is the signed value, hexadecimal signed 2's complement shown in a hexadecimal notation. So this is minus 5 and so on. So when we perform loop, it will automatically add this offset, to inside the program counter. In some cases, when we use flat memory, so it has direct address, because there are no segments. There are no segments, only direct address. So it will have the direct address like 0, 0, 0, 0 something, or F7, 1, 2, 3, 4 are these 20 bytes, 20 bits or 32 bits, whatsoever the address size is. So it has complete address in that case. If we use the real mode, then this one will be different, and protected mode or flat mode, then there'll be complete address and so on. So this loop will move backward to the this address L1, the address which is shown as a L1 and so on. So this is the loop. Now what will happen here, I think that was the logic that we discussed. Now what we are going to discuss here, what will be the operation. So initially you can see here the move AX is equal to 0. So we discussed the program flow. Now we are going to discuss what will be the output of this code, these 5-line or 4-line code. But previously, continuously we were discussing about the flow control and the logic and so on. Flow control. Now we are going to discuss what will be the operation that is being performed by the loop example. Here you can see ECX is equal to 5. Okay, ECX is assigned 5, AX is assigned. So I want to just write it here in the first time when we are moving. So we have ECX is equal to 5 and ax is equal to 0. Now ECX is equal to 5 and ax is equal to 0. So first time in the first execution, what will happen, add ax comma cx. So ax comma cx. Now you know that we assign 0, 5 or 5 decimal value or hexadecimal, doesn't matter right now, because 5 has the same notation, hexadecimal and decimal. So what we do for the ECX, we just only take the value of the CX or 16-bit register. So 5 value will be here. This is complete ECX. So ECX, we are taking the part of this ECX. So 0, 5 is stored here, and these all will be 0, 0. Okay, so what will happen here, so ax will be added with the cx. So ax will be equal to 5 initially when first time we execute. And what will happen here at the loop, this 5 ECX will be subtracted and decremented. So ECX will be decremented. ECX is equal to ECX minus 1, which was a logic. So ECX is equal to ECX minus 1, and this value will be transferred into the ECX. So the new value for ECX will be 4. Now we have to check either ECX is not equal to 0. If ECX is not equal to 0, then we will jump. So definitely ECX is not equal to 0, so we will jump here and again perform the execution. So this time ECX is equal to 4 and AX is equal to 5, so we add them. So ECX and AX are being added again. So this will be 5 plus 4. So again it will be AX will be 9 and so on. So it will add 5 with 4 with 3 and 2 and 1. So when ECX is equal to 1, what will happen? It will decrement at this point. It will decrement, and in the ECX, definitely if you decrement 1 from the ECX, the result will be 0, and 0 will be stored in ECX register. And if the condition is not true, then what will happen? For example, if the ECX is not equal to 0, so condition becomes false right now, so this will not jump. If the condition become true, like ECX is not equal to 0, then it will jump. If ECX is equal to 0, it will never jump, and so on. So what will happen? It will move in this direction, forward direction, and so on. Okay, so we are going to move. If the relative offset is encoded in a single sign byte, for example, हमारा जो offset होता है, either sign byte means either हम negative में offset हो सकता है, positive offset हो सकता है. What is the largest possible backward jump? Single byte, 1 byte. अगर 8 बिट्स हैं और उसमें से 1 बिट जो है वो साइन का भी है. So what can be the backward and forward jump? Backward means ऊपर की तरफ jump, और नीचे जो है ना forward means अगर हम आगे की तरफ जो jump करना चाहते हैं. Okay, so forward jump means current location से नीचे जो प्रोग्राम लिखा हुआ है वहाँ पे jump करना है. Backward means जो current instruction execute हो रही है उससे पहले जो instruction से वहाँ पे अगर jump करना चाहते हैं. So what should be the possible backward jump and forward jump? The easiest solution is, if you know that what is the maximum value, maximum positive and negative value, that will be the answer. So answer is minus 128 and plus 127, 2 raised power 7, and then this is the maximum value in positive, and then we have the negative value. 2 raised power 7 is the maximum value in positive, and the negative value is minus 128. Okay, what will be the final value of AX? You can see here. What will be the final value of AX? Increment AX here, and we are going to. So here AX is equal to 6. ECX is equal to 4. Okay, now increment AX. So AX will be, initially it will become 7 for example, and we will decrement here and it will be 3, so we will jump again, then it will increment again, so it will be 8, and decrement again, so it will be 2. ECX will be equal to 2, it will jump again and it will increment, so it will be 9, and so on, and it will be 1 again and it will jump again and it will be 10, and so on, and then it will be 0. So what should be the final value for this one, and how many times this loop will continue if ECX is equal to 0? Because when ECX is equal to 0, just remember one thing: if ECX is equal to 0, definitely initially what will happen at this point, before jumping we decrement. When we decrement from the ECX, definitely this will be the negative value. This will be the negative value. So what will happen? It will jump because it is not equal to 0. So it will continue up to how many times? So this, the answer is 10 for that one, we already know. How many times this loop will continue? It depends what is the size of the register. It can be that much number of times. Okay, and the loop will execute because we are continuing for whole negative numbers, all the negative numbers again, when it will become 0 and so on. So just try to avoid this one. So here, how many times the loop will execute for this one? Infinite times. Why? What is the reason? For example, there is a logic. Before means here we decrement ECX. ECX is decremented. ECX is equal to ECX minus 1. Okay, whatsoever the result is, that result is transferred to the ECX. But before decrementing, we are incrementing. Before decrementing, we are going to increment. So what will happen? ECX will remain same. It will remain same because we are incrementing before and then we are decrementing. Here, for example, move ECX comma 7. It will always remain 7 because here we increment, it will become 8. Here we decrement, it will become 7. Then we will jump. It is 7, then it will become 8, and then again it will become 7, and so on. So this is the, just try to avoid these. Then we have nested loops. So if you need to code a loop within a loop, means nested loops. So for example, here you can see we have L1, we have L2. So this is the loop, and in a loop this one is the outer loop. So this is called nested loops. So if you need to code a loop within a loop, you must have to you must save the outer loop counters. ECX value, it's better to save because ECX is required for this loop and also ECX is required for this loop. So what we have to do, move, we have one variable here. What we do, before going to move here to the inner loop, we save or move the value of ECX to the count. This is the variable where we save the ECX. So when this loop finish, because this, before executing this loop, we again say initialize ECX to count something and so on. So what will happen, before initializing a new value, we have to save the previous value, and when loop will complete its execution, again load the value from the memory where you saved the value of ECX and so on. So this is one example. In this example tells, this is the same example which we did in our previous lectures. So we have array. How many elements of array are there? There are like 4 elements. So now we want to add them. Initially what we did, we were using indirect addressing and so on. We were adding all those elements. Now we know that what is offset, value of offset, what is length of, and we want to add it. We want to add them. So this will be the result. This register will store the results. Now here you can see EDI has the address, starting address for this integer array and so on, and then ECX is the length of means how many elements are there. So elements are 4, so 4 elements or 4 value is stored in ECX. Now what will happen here, so this is indirect addressing. So EDI is added with the AX. Okay, so we add the first element to the AX. So initially AX is equal to 0, and we add 100 in hexadecimal, so it will be 100 in hexadecimal. Now we add what we add the type of integer array. So how many times what is the value we are going to add? We add 2 because this value occupies 2 bytes. Then we have to move to the next this byte, this element. So we add 2. So this whole expression from here to here, it will give us the type, and type is word. Word means 2 bytes. So we add 2 in the EDI. So EDI is added. So now the value of EDI is, for example, it is the incremented with 2 or added 2 in this address, and again we loop. Now before going to perform any loop, ECX was equal to 4. Now ECX will be 3. Now ECX will be equal to 3, and so on. So now ECX will be equal to 3, okay, after decrementing, and then we will perform loop. So the second element will be added into the AX, okay, and after this one it will be 2, then third element will be added, then it will be 1, then fourth element will be added, and this will become 0. If it will become 0, so the loop will terminate. So we can add all these elements. So this is a logic. You can perform, you can do anything that you want. You have now looping statement, you can perform add, subtract. We will do other instructions, how to perform multiplication, division, and other comparison operators and so on. But here you can see now the same program, which was very long program, there was no logic, just directly we were accessing. So here is a small loop which can execute infinite, not infinite, but the some number of times which we mention in the logic, okay. But if this number exceeds the like 200 elements or 300 elements, you saw that in previous example the code size will exceed, the code size will exceed if the number of elements exceed. Now here this is the only loop which will perform addition of how many number of times, whatsoever the number of times this loop, this size of the array is, it doesn't matter. So now we have concised the code and so on. So in this, now we are going to summarize this lecture. So in this lecture we discuss about the instruction execution cycle. We saw that what are the components inside the computer which are involved in the instruction execution cycle. Then we also discuss about the program execution, and then we discuss about jump instruction and loop instruction and so on. So inshallah in the next lecture we will discuss about the practically how we can perform all these operations inside the assembly language, and we will see what will be the actual representation of all these codes inside the assembly language. So till next lecture, Allah Hafiz.